All right. Hi, everyone. Welcome to the Earth Science Classroom. We're looking at the outer core and the Earth's interior series. We're looking at the EM field. This is our second video on that. In the first video, I discussed the basic characteristics of the outer core being molten. There's turbulent convection, the depth, the temperature, the pressure, the composition of mostly iron, nickel, and a little bit of sulfur. And that sulfur creates a lowering of the melting point, allowing for the outer core to be pretty much liquid, and that was proven by the lack of S wave propagation through this layer, and also the Gutenberg layer, which saw a very distinct discontinuity of the P wave velocity going from 13.5 kilometers per second down to about 8, and it's slowing down through that liquid layer. So look at the EM field, and EM stands for electromagnetic field, and this is created or generated or sustained, and the origin is from the outer core. Now, basically, electricity is simply enough the flow of electrons. And this basically relates to its charge. So we get the basic atom that you'll see in most textbooks, right? You have the electron flying around on the orbital shell, and based on the size of the atom with the amount of protons, you're going to have also the nucleus in here. The nucleus will have the proton, and it'll have the neutron. Neutron has no charge, the proton is positive, and the electron is negative. Now, you can have more electrons and more protons, but you can have also an anion or a cation, as well as variations within that atomic structure. And this by itself is basically the movement of this electron on its shell as it buzzes around the nucleus creates an electric charge, electric current. So by natural causes, each individual atom has its own electrical charge, and when you add atoms together into molecules and compounds and materials and the outer core's composition, which is iron and a little bit of nickel, that these guys are metallic. It is an iron alloy, and these are both ferromagnetic elements. So they are naturally magnetic. Now, what does that mean? Now, magnetism is the separation of the positive and the negative, and creating a force that would either repel or attract based on the charges. Now, we all know from grade school and younger grades that if you have two of the same charges, they will repel and push away. And if you have two of one of the negative, one of positive, and we have the different, then it would be attraction. And that basic magnetism between the charges. So most things do create this magnetic polarity, this difference where you have separation and you have what's called poles that are created. Now, north and south, and you think of a compass, but you can also think of a bar magnet where you have, the long bar, and one end is north, one end is south, and the experiment where you had like the iron filings on the table, and it makes that beautiful, beautiful design pattern, and you see how the magnetic field is created and generated, and the iron filings would represent that in its shape. So I also put here common ground. Now, the cool thing is that in physics, that any moving charge generates a magnetic field. So the movement of the electron actually creates, obviously, electric current, but at the same time, movement of the electron creates a magnetic field. So these two are like joined by the hip physically. Even though structurally it can change, physics, they're basically, hand in hand, basically. And the scientist that really established this or discovered this was a Danish scientist by the name of Ørsted in 1820. There we go. And it was developed further. So he basically found the relationship between these two natural phenomena, and then it was taken further and developed for more applications by Faraday, and also a guy named Henry is also said to have done the same thing around the same time, and this was in 1830. So the knowledge of this and the application of this has been around for pretty much 200 years, and this was basically to do with magnetic induction. So high-powered magnets that are electromagnet, where you could flick a switch and they could turn on, turn off, and it was very functional, especially with a lot of the materials being iron, being metallic. So let's jump into the Curie point. Curie point is the temperature at which naturally occurring magnetism from ferromagnetic elements or materials gets diminished. So it is 770 degrees Celsius. Now, iron's melting point is a lot higher. That's the melting point. So we know that a partially melted iron stops being magnetic at 770 degrees. However, if the iron was at 660 degrees, let's say, then it's still in its non-melted solid state. What we have is it's magnetic. So what is it? Basically, you got this big block of iron, and you have all of these electrons, and when it's colder or solid or it's magnetic, what it is it forms in these same lines. So these electrons and the charge is all pointing the same direction. They're all aligned. And that kind of organizes all of the tiny electric currents and tiny magnetic fields into the same direction, say this way. Therefore, it kind of develops into a much stronger magnetic force when they're all aligned or organized, and that's what happens with iron that's below this temperature. However, if iron is above this temperature, let's say iron is 1400 degrees Celsius, because it's partially melted or going to be melted or going towards melting, it would start to reorganize or disorganize the electrons and the atoms within the iron, and it would not be organized, and the magnetic force would be all over the place. It wouldn't add upon itself and become stronger. It would basically cancel out with opposing forces in different directions. So it wouldn't really work in terms of being a magnet anymore. So this Curie point is important. However, When you apply this into the outer core, which has temperatures well above the melting point of iron, but you have also the intense pressures, you do have that molten material, but because of the um, turbulent convection coming out of the inner core with intense heat and energy being moved out of the inner core into the outer core, and you also have the coriolis effect and the Earth spinning. And this is a liquid, so it's not attached. You do have like the same effect as you get with hurricanes or typhoons in the atmosphere on the surface. They're going to spin in a certain direction based on the hemisphere it's in because of the coriolis effect, the effect of the spin on these liquid and gases. So the whole outer core is spinning, and this is movement. And the movement in one direction, which is very important, but not the band, but the actual direction in which it's moving, it creates that even though it's a really high temperature, you might get this unorganized, unmagnetic or non-magnetic material. Because it's moving, you're going to naturally align all of the iron particles and electrons within the iron in the same direction, therefore creating this very, very consistent one-directional kind of self-increasing, self-developing, building upon itself magnetic field and the charge as well. So this is how the Earth's electromagnetic field is generated, because of the movement and spin. Now, it's not perfect because you've got these turbulent convections and you've got these small like eddies inside of the outer core, and it's slowly moving around, but there's definitely fluctuations. So the magnetic flux, as they call it, is not consistent, and it varies substantially with time. And we'll get to that in the next video, is what actually happens to the EM field because of this. But this is how it's generated. The iron is molten, therefore it's moving in a liquid phase, it's flowing through convection, through Coriolis effect, and the alignment and organization is caused by the movement, therefore creating this EM field, which is pretty awesome. Like this video, guys. Please subscribe. I hope this kind of clarifies a few things, going from the basics of physics in and applying it to our outer core. And the next video we'll look at what this EM field looks like, how far it goes into space, and the effects.